Alright, so this video was supposed to actually be made like last year, but I just didn't feel like making it. So we're making it now. So yeah, this is my 4-bit computer basically. So we got our read-only memory, RAM, the CPU is right here. We also got a custom-made video card. Well, all this is custom-made except for the ROM and RAM, because that actually not work, because Logisim isn't that optimized. And for our ROM, we got a whopping 2 kilobytes in total. It can't have any more than that. And for RAM, we upped it up a bit more. We got 128 bytes of RAM. But going by bytes is not good for this, since it's a 4-bit computer, so it uses half a byte for what it calls a byte. So it's actually 256 half bytes of RAM and 4 half bytes of read-only memory, or ROM. So the CPU itself, it has 16 opcodes, which are basically the instructions it's even able to do. So you could increase the number inside it, or its accumulator, decrease it, load numbers, add numbers, mostly just basic stuff. I won't get into it right now. But we also have the video card, which is basically just a bunch of serial, a lot of them, a bunch of basically, what's it called? Serial gates? No. Shift registers. It's just basically a big shift register in 2 dimensions, meaning you have to load each pixel manually. Not the most efficient, but it works for our case. And this video card allows for a 15 by 15 display, which is this thing. So if I just load a program and run it, you can see you get you can draw like a smiley face or something, really bad one. And each one, all it does is basically you write line by line for each pixel, and it's vertical for some reason. I forget why it happened like that, but there's just basically a bit for updating, a bit for a clock, and 4 bits for entering whatever number from 1 to 15. And there's a reason why it's not a 16 by 16, which is that 0 cannot be a pixel number, or else it will always draw on the 0 line, and you don't want it to. So yeah, that's basically the computer. We also got other stuff, like all this is just basically going into the RAM to add options for like a joystick, which I'm pretty sure like things like the NES did, where they just plugged it directly into the RAM with another chip, and you just read from RAM to grab it. So if I were to load an image, which is PONG, and then reset it, because you have to reset it every time, it's actually very slow unless you set the frequency to max. But it is a working Pong game, so it's 1-player Pong, because I'm not spending that much time to make 2 players. But if you move the joystick up, the thing will actually go up, and if you move it down, it will go down. Stop. It will take a while, but it will stop eventually, since each input is like 1 frame. And also the ball can miss, and if it misses, it'll just spawn back here, because if it spawns in the middle, it's too obvious. So I'm just gonna play a bit of this to kind of show what the Pong's like. So yeah, that's the CPU at work at its max speed, which is 4.1 kilohertz. Can't go above that. Not physically possible. So next is how it works, I guess. Alright, so the CPU may look a bit complicated when you zoom out, but it's honestly not that complex. It's actually quite simple. So for the basics of a CPU, there isn't really much you need. So you really need 3 parts, technically 4. So first, you need an arithmetic logic unit, or ALU. So basically, you just need a calculator, something that can do the math, all of that stuff. And then next, you need a control unit, which basically converts the signals, like all the ones and zeros, into actual instructions that are in the CPU. So it's in control of, like, it's in control of basically converting, like, from the ROM, from memory, converting that into programs, into an actual instructions. So yeah, that's why it's an instruction manual. And we also have the memory unit. That's not what it's called, but I'm calling it that for now. And that basically deals with all the other stuff that isn't, like, math related, that needs the arithmetic unit. So this one deals with, like, things like putting stuff into memory, like saving stuff into RAM, copying things from RAM into memory, or no, copying things from RAM into the CPU, and, you know, reading back and forth, stuff like that. So, and then we also have the accumulator, and this thing isn't really a component, but more just kind of important thing where it's basically just a number on the CPU. Mine only has 1, but usually CPUs have like 16, 32 of them, and this is where all the math stuff ends up going into, and also the memory stuff. So basically the accumulator is connected to both of these things, and it's how basically the CPU saves its math. Like, if you want to do like 1 plus 1, you save that 1 in the accumulator, and that's all there is to a CPU. But when you look at the actual CPU, you can see there's a bit more than 3 components here. Like, you can see the ALU right here, and here's the accumulator. Currently it has 1 in it for some reason. But, like, and also here's the control. This is technically the control unit. But what about all this other stuff here? Well, it was kind of a generalization to say there's 3 components to a CPU, because it's 3 main components, but there's also a bunch of other stuff that it will not function without. So I'm not going to explain this entire thing, since I don't even know how it works. Like, all this just looks like spaghetti to me, since I kind of just went through it bit by bit and did not look back, and didn't bother trying to make it look nice. So we're just gonna go through step-by-step basics of how you can go from the most basic components to building this CPU. So starting from the basics, we start with 3 basic gates: an AND gate, OR gate, and the NOT gate. So how these work is exactly what it sounds like. So for the AND gate, just as it says, the output of this will only turn on when both this input and this input are on. If either of them are off, the output turns off. So it's just when this and this are on, this turns on. And for the OR gate, it is just if this is on, or if this is on, then the output will turn on. And both of them are, and they'll still stay on. The NOT gate, which is very important, it just inverts the signal basically. So it would take the opposite of what the input is. So if this is off, then this is on, this is on, this is off. That's it. And those are the three basic gates. Now if you put the NOT gate in front of the output of the AND and OR gate, we get NAND gates and NOR gates, which basically do the exact opposite. So, because the signal's inverted. So now this thing will turn off when these are both on, and this one will turn off if either of these are on. If you take a NAND gate and you mix it with a OR gate with a AND gate, what you get is an exclusive OR gate. So now it acts like an OR gate, except if both of these are on, this turns off. This XOR gate is actually pretty useful, since this can help us make a basic bit adder. So normally if you wanted to add 2 bits, you would say if you have this one and you add this one, you'd want that to be equal to 2. So let's just say this is 2 and this is 1. So that would mean this add this is 2, because 1 plus 1, and if you just have one of them on, you would just say this one. But obviously, since the OR gate turns on if both of them are on, you end up having it say it's 3 when you add 1 plus 1. And 1 plus 1 is in fact not 3. Not even close. So, by using an exclusive OR gate, now this thing is fixed where if you just have 1, 1 plus 0, 1. 1 plus 0 is 1. But 1 plus 1 is 2. And this is a bit adder for 1 bit. And since we have a bit adder, why don't we just make a 4-bit adder then with 4 of these? So if we just make, I'm just gonna make a new circuit for this one. So we got our bit adder, and if we just took 4 of these and just place them all together here, we should theoretically get a 4-bit adder, right? So with this, now we can add 2 4-bit numbers. So 1 plus 1, 1 plus 2 gives you 3. 1 plus 8 gives you 8 plus 1 is 9. 2 plus 8, 10, so that works. But we have a bit of a problem where if we add the same number, like 2 plus 2, it goes to 0, since this 2 ends up saying it's 4, but the 4 isn't connected to something. And you may think we could just put an OR gate here. So if we just took this and then move it out to here, because now we have 2 plus 2 equals 4. But then we run into another problem, which is if we have 2 and 4, that's 6, and we add 2, we're still getting 4 for some reason, even though it's actually 8. Or if we have 2 numbers like 3 plus 3, it should be 6. As you can see, it's still highlighting this one, but it isn't 6. And the problem is that we can't just OR these together. We have to carry the number. So in this case, carry the 2 from here to the 2 here. And it's actually pretty simple to do this. All we need to do is make this instead of a single bit adder adding 2 bits, we make it a 3. It adds 3 bits together. So a bit adder with 3 inputs. So we basically just do the same thing we did with the first two and combine it with an XOR gate. So we just connect the XOR gate of this one to this one. So now if any of these are pressed by themselves, this will turn on. If all 3 of them were pressed, it'll still turn on, since the first gate cancels out the second one. And then we just add the carry in by having an AND gate with the carry and either of A1 and A2 together. And since this AND gate or this AND gate won't be on at the same time, there's no need to make this one an XOR gate. We can just say this and this together, this or this one is on, and that gives us a 3-bit adder. So 1 plus 1, 2, plus 1 is 3, and this works for any of these. So now that this has been modified, it's going to be giving us errors on this because we're missing an input. But now we can ignore this one. Well, actually we can't ignore it. We can just put a constant 0 here, so that won't yell at us. But now we can just take the carry, or we can take the output of the second one and put it into the carry of the next one. We just keep doing this, easy looping. And now our adder has been fixed. So 3 plus 3 is 2 plus 6, or 2 plus 4, which is 6, which is right. We could say 8 add 4 is 12. Well, that doesn't work. If we have 12 add 4, we get 16. And if we were to add all these together, so if we have 15 add 15, we get 16 add 8 add 4 add 2, which is 30, which is also right. So this is our 4-bit adder. And we could add another carry, but I'm not making an 8-bit adder or anything like that, so it should be fine with just this. Now with our 4-bit adder, using some properties from it, we can actually make a 4-bit subtractor. With a 4-bit subtractor, it's basically just 2 4-bit adders. And when you take, to subtract, all you do is you take the inversion of what you're subtracting from. So right now we're subtracting it's A subtract B right now. And if we just take the inverted signal of all these, and we add 1, what we get is basically a subtraction from addition. So 2 subtract 1 is 2. Let's see, 4 subtract 1, 3. 8 subtract 4 is 4. if we do 0 minus 1, we get 15, since, like all computers, if you go below 0, you end up at your highest number, which in this, or at least back to the highest number, in this case is 15. And what we can also do is a little trick that I figured out by accident, is that the one input or one output from this that we just ignore, if we actually take in this, if we take this output like that, put a NOT gate in front of it, this basically tells us if it's positive. So that means if, for example, you want to actually have negative number, it doesn't actually tell you if it's a negative number, it just tells you, or what the negative number is, it will just tell you that it is a negative number. So in this case, it thinks 0 is negative, which is fine, I guess. But, so if you have like 1 subtract 2, that's negative, 1 subtract 3 is negative, 8, 5, any of that, but 2 subtract 1 is positive. So, and this negative output may seem kind of useless right now, but it's actually very important for one of our instructions. And I realized just now that I didn't actually explain what an instruction is. So basically, an instruction is like a little circuit that has one thing it needs to do, and it gets assigned to one of the 15 numbers from the 4-bit CPU, since 4 bits is 16 possible numbers, but 0 just gets to be nothing. And each of these gets assigned to one circuit that will do something to the accumulator here. And our most basic opcode, or our most basic instruction, is the increasing and decreasing. And these things, if I just find it, are in the ALU. And all it is for increasing and decreasing is literally just those adders and subtractors, and it just adds 1 to whatever the input is, and that's it. And there's also a thing that just inverts it, that says to use adding or subtracting. It will not be touched. It won't let me change it, but. And this also brings us to the other thing. I don't know why I just did that. It also brings us to our other instruction, which is adding and subtracting numbers, which is just this thing, which is same thing, just an adder and subtractor mixed together, the exact same thing as before. Now that we've gotten 2 of the instructions out of the way, technically 4, we are going to go back a bit to our NOR gate. Now, this NOR gate is kind of special, since if you were to take a NOR gate and you connect the output of one to the one of the inputs of the other, and do the same for the other one, what you get now is when you turn one of these on, this thing stays on, and when you turn on the other one, this one turns on and stays on. So if you had 2 outputs, or you can just say one output, we don't need both of them. So if this were an input and output, actually I'll connect it to this one, because it'll make more sense. So if you connect it to these, this could be seen as a set, which sets the bit, and this erases the bit. So this sets it, this erases it. And this is basic memory. Or yeah, it's basic memory. So 1 bit of memory. So you can either set it to be on or erase it to be off. And you can also do this with NAND gates, but I kind of don't remember how to do that, so I'm not doing it with that. And what this is called is a JK flip-flop, which is basically this thing. And for our CPU, it's not really useful. So it'd be nice if we could just have set and erase on the same pin, right? Or on the same button. So we can do that by adding in a clock. I'm just gonna call this. And basically have it so this thing only updates whenever the clock updates. And to do that, all you gotta do is you just connect the set/erase button now with the clock with an AND gate, just having it inverted for this erase. So now, turning this on and off doesn't do anything, but when you update it, it will go to either on or off, and if you turn this off, it releases. So now we have something that can set and turn off something with just the pulse of a clock. And this is a D flip-flop, so it just has an input for a clock and an input for the signal input. And also these things down here, which they can just set it to on or off, which you can just add, which would probably just be something like this, where you just put another OR gate so that it can be this signal or this that turns it on. Like so. So now this would just automatically turn it on. And these things are also very useful for like clearing memory. So, but I'm not gonna put it on this one. All you know is that this D flip-flop basically leads to everything doing with memory on the CPU. For example, this is how the clock or the counter of the CPU works, which, if I just make the simulation speed just a bit slower, you can see it counts in binary. That's still a bit too fast. So this is counting in binary, which is important because this counter basically just goes through all the addresses of the ROM in order, and the RAM at the same time, technically, and takes that as the input instruction. And that's one of the things, and this is also what the accumulator is. So actually the accumulator isn't here anymore. The accumulator is up here now, which is this thing. And oh, it is in the this is the accumulator basically. So any number that has to do with anything ends up in here with this 4-bit or 1/2 byte number. So whenever it increases, it'll increase this thing right here. And it's also how to make basic memory. So the RAM of this, which is outside here now, could actually be made using those D flip-flops, just in like a sequence. Of course I didn't do that because that would actually crash this, since that's too much processing. But yeah, that's what D flip-flops can be used for. Now that we've got all of our basic components, we can actually use these to make the rest of these instructions. So let's start with all the ones that use the D flip-flop, or in other words, the single byte, which I call the 4-byte. It's just 4 of these together. with this, we made basically all of the memory type instructions, which are the loading, storing, jumping to another instruction, and comparing. All of those use the flip-flop, the flip-flop, and also one instruction that's in the accumulator, which is the load into a number, instruction number 3, which is this one. Yep, goes right here. So all this does is it just copies whatever here to whatever is here. And that's why I said that having a constant 1 and 0 that can easily be plugged in is very useful, since you can just use that to set it exactly to this instruction, or set whatever number you want immediately. And we also have our bit more complex things, which is down here, and it's these two. And these are important for the instructions that aren't just one cycle of the clock. And a clock cycle is just... Where is the clock? Alright, so here's the clock. So, yeah, all one clock cycle is basically just this thing turning on and off. Because whenever it does, then the counter over here goes up by 1 bit, or just goes up by 1. So, anyways, the instructions that take 2 clock cycles, or 3 clock cycles instead of 2, are these ones. And these ones also, which are here, take in 2 bytes of memory, or technically 1 byte. So 2 half-bytes of memory. I was going to call them 4 bytes. It takes 2 4 bytes of memory in. No, 3. Because it's 1 here, and a third one down here, I think. They're not in the right spot, but basically this is the reason why the RAM can only go up to 256 while the ROM can go up to like 4,000, and that is because these instructions, which are used by the ROM, can go all the way, can have it jump, like the jump instruction can jump all the way to 3 4 byte numbers would be 2 to the power of 12, which is 4096. That's what's 4K. So that 4096 possible numbers to go for the ROM, or 4096 possible bytes to go to, and since they're 4 bytes, or 4 level bytes, it's technically 2 kilobytes. And the reason I didn't connect the RAM to that is because I didn't want to, and because that makes it faster, since the loading and adding to, or loading from and storing to RAM functions are only 2 clock cycles, which is way faster. Anyways, yeah, so for the storing and loading into address A, it uses 2 4 bytes to store the address where it needs to go, since you can only do 1 byte at a time, so it needs to store 2 of those for the 2 byte address, and it needs 3 of them for for the jump instruction, since that is for jumping through ROM. And these 4 byte things are also used in the compare instruction right here, which is like basically if you do programming, it's like an if. So basically if this equals this, This is the if part. And all it is just another 4-byte that has a bit less stuff on it. So it just has something for clearing and enabling it. And it's the 4-bytes used in anything that requires you to store a number, basically. And looking back at the arithmetic unit, seems I forgot about two kind of important, not really important, instructions that I failed to mention, which are the left shift and right shift. It's because they're very easy. All it does is moves all these bits to the right or to the left. That's it. And it's pretty simple. All it is just a bunch of AND gates put together. So, let's say number 7. She goes up to here. Oh, it's right here. Yeah, all it is just a bunch of AND gates that makes it so that all these numbers move to the right or left, and I don't think it really carries, even though it does, it's supposed to, but it can technically carry the last bit that gets voided. So our last instructions to look at are our comparison types, which are the few ones that are actually labeled, and that is the break on less than, break on equal to, and break on greater than, and there should be a fourth one somewhere. Oh, it's right here. It's basically a break on not equal to, but I just made it so that it just inverts the signal here. And these ones, the break on equal to, pretty simple. It's just, does A equal B? If it does, out. And not equal to is just an inversion of this. But our break or greater than or less than, use the special feature from our subtractor. If you remember, the thing that tells you if it's negative. Since, to figure out if a number is greater than or less than a number, if you were to subtract the smaller number from the bigger number, it will always be negative. So all you need to do is check if that negative flag is on. And you do the same for both of these by just swapping them. You just swap these inputs, and that's all it is, just the subtractor. And just checking if the negative sign is on. And I also took into account if the number is not 0 as well, since 0 could be a problem. And that's basically it. Those are all the instructions. There's also some special things. So if we look at all of the instructions and how long each takes, or the cost of each one, so how many clock cycles, increase and decrease take 1, so does the none, since nothing happens during that one. Loading a number into the accumulator is 2, so 1 for just the instruction and 1 for a number. Same with adding and subtracting. Left shift and right shift are 1, but loading an address into the accumulator takes 3, since you need to load a 2-byte address. And same for storing. Jumping takes 4. Comparing a number is just 1, since it's just, actually no, it's 2, since you're just comparing it to a single byte. Breaking on equal is 4, since all these breaking just do a jump instruction. It's basically just a jump instruction, but with a condition. And there is a bit of a problem with how this works, which is that it is very expensive just to load an address, and there's a lot of loading addresses if you want to actually do something with the CPU. So I added 2 special features, which if you store anything, so if you use store A onto the address FF or FE, then it will set it to either address mode on or address mode off, which is this 1D flip-flop right here. And what that does is basically numbers the numbers 0 to 15, instead of just being a number, whenever you load into A 0 to 15, instead of just loading the number, it will look at RAM address 0 to 15 and instead use that. And same with everything else that loads a static number. So if you, it basically affects, what says right here, it affects the parameters 3 or the instructions 3 to 5. So adding to A is adding that instruction, adding that RAM place, and subtracting is subtracting that RAM thing. And that basically increases it to have 15 more accumulators basically, which is very useful. Oh, and also it affects compare. So it will compare to that RAM address. And this is very useful because it brings down the CPU time to do literally anything by like half. Since it's not using 4 now, it's using 2. And that's actually it. There are some problems. Like, for example, somehow I accidentally made all the numbers backwards, so when you're actually loading like a number from RAM, like here for example, if you want to load 02, you say 920, so load the address 20, and it's basically little endian, I think that's what it's called. And I didn't want to do it like that, but it just ended up being that way. So that's one thing to be accounted for. And that also means that for all these things which I added for writing to the video card, it's actually like load 0f since it's all backwards. And all this stuff is just, I don't know if I mentioned before, it's just basically decoding from the RAM. And since I can't talk directly to the RAM with this, I just wait until I load or store something from the address and then read it then, and that's fine for what this stuff needs to do. And the same for the joystick. And yeah, that's it. The CPU. Alright, I actually lied again. So I didn't mention this because it's kind of hard to talk about, which are jibs, which are these things. And they're a very bizarre thing that's added to the CPU, but this thing will not work without it. I don't really want to explain it too much, but basically it's like a network basically where they make sure you don't accidentally run 2 instructions at the same time. For example, on the CPU, if you wanted to load the number 3, you'd have to type 3, and you don't want it to accidentally just do the instruction 3 and then do the instruction 3 twice. Or if you wanted to like add 3 to whatever, to A, you don't want it to accidentally try that instruction and then cancel it with another 3. And basically the jibs connect to each other. So if I click on this, it's connected to every single other jib. It is just a network of jibs, and that was my bad way of fixing the problem of instructions going into each other. So it's connected even to this, it even connects to the ALU in some way here, to all the other jibs and to other instructions to make sure they're all disabled. And yeah, basically all it does is it disables any other instruction once one instruction starts. So once this one would start, for example, it would call out to everything else that it is enabled through this chain of OR gates, which goes across the entire CPU, including the ALU. And that basically makes the CPU work. So jibs save lives.